In the previous section, we learned about action problems, and in this lesson, we're going to extend that by looking at the remaining problem types that first graders are expected to solve. And these problems that we're talking about today are non-action problems. This is the remaining part of the chart that you saw in the previous presentation. This is the bottom half, the additional problems that first graders are expected to solve. The top category, put together, take apart, is also called part whole, which I find a little less of a mouthful than put together, take apart. We'll be looking at that next. The bottom is compare problems, and I do want to note that compare problems represent a brand new class of problems for first graders. They haven't had any experience problem solving with that context necessarily, and so that's new and different. Also, the language elements embedded in compare problems make them often quite difficult for children. The two variations that are in the red boxes are not necessarily going to be achieved to mastery by all your students. So although first graders are expected to work with those problems, there is a recognition on the part of Common Core that mastery will probably be, for some of the learners, not achieved till second grade. Okay, so this is the top image from the chart we just saw, and I want to begin by talking about how this problem context or structure is different than the action problems. In the action problems, there was a chronology, a start quantity, then a change, and then a resulting quantity. Here, that is not true. There is simply a whole and a couple of parts. And so in this case, if you look at the total unknown, there's apples, a group of apples. Some are red, some are green. None are being sold, none are being eaten, none are joining the group. I didn't buy any more. It's just some are this and some are that. So it varies. It's different than that action sequence. The total unknown and the both add-ins unknown were actually introduced in kindergarten, so they should have some familiarity. However, first graders are expected to continue working with these problems. You might use them by extending the numbers they're comfortable with. The both add-ins unknown, they should easily be able to decompose, in fact, fluently decompose numbers up through 5 in kindergarten, and had experience decomposing up through 10, and that fluency level with decomposing up through 10 definitely needs to occur in first grade. So continue to work with those both add-ins and known problems. We're going to take a look at the middle problem now since it's new. Before we go to the next slide, let's look at the problem. 5 apples are on the table, 3 are red, and the rest are green. How many apples are green? Note that the whole group is 5. We do know the value of one of the parts of that group, the 3 red apples. The green apples are a question mark. We don't know the quantity of the green apples. Children often struggle with these add-in unknown problems, and so part of your means of supporting them best will include making sure they're really comfortable with pulling numbers apart and putting them together. If they really have a strong understanding of what it means to pull a number apart into 2 parts and then put it back together, that will be very useful. So all the work they've done with decomposing number, like finding out that 5 is 1 and 4, and 4 and 1, and 5 and 0, and 2 and 3, and 3 and 2, and being really comfortable with pulling it apart in multiple ways, that's going to be one of the ways to support children with add-in unknown problems, is having that rich background in trying to put together and take apart numbers. The second way is visualization, and this is going to be a theme, I think, in this presentation, that one of the primary means of supporting students in problem solving is supporting them in visualizing the problem. 9 times out of 10, the problem itself isn't so much with the numbers, it's with visualizing the relationships that are embedded in a problem. When a child can visualize what's going on and what the relationships are between the elements in the problem, usually they're able to be successful. But when they can't visualize those relationships, typically they struggle terribly. So in supporting learners to problem solve, one of your primary tools available to you is supporting them in how to visualize the relationships. We're going to be talking about 2 tools for doing that. The top tool is called a number bond, and initially we label these circles or squares whole and part so that they are aware of what we're talking about. Eventually, just the structure itself of a number bond doesn't require them to have those labels. They can see which ones are the parts and which one's the whole. But in this case, what's the whole group of apples? What's that amount? It's 5. And we know one part. We know the 3 red apples. And we don't know what the quantity is of the green apples. So we can use this number bond. And although I have numerals here, you could actually put apples in the into these. You could have, like on smart boards where you're using icons, and you could put the actual quantities of them. And then the tape diagram below, it also called bar model in Singapore math. That's another way. You can see we have 5 apples here represented by red squares, and 3 of them we know are red. I could have labeled it 3 red, and then we have a question mark for the green. But the model itself, you'll see, is very clear about what's going on, and can be a real support for learners. I do want to say one thing about both add-ins and known problems before we move on to compare problems, and that is something that the Common Core authors have been very specific to point out, and that involves writing equations. If you look at the image here, this was done with a group of kindergarten children. They were decomposing 5 into different values. Actually, they had a little story about apples, and so they were finding the different combinations they could have of red apples and green apples. And then in the column behind that, you'll see that I was modeling for them how mathematicians write that. Essentially, what I have there is an expression. There's no equal sign. It's not an equality. It's just, or an equation. It's just an expression. But if I were to turn that into an equation, which becomes a really important aspect of how we are extending students in first grade, is really extending them in writing equations. Children often assume that the whole always has to be on the right of an equation. That's a completely erroneous assumption, which children arrive at because they see such limited examples. If a teacher always writes the whole on the right, then students assume that it's like some requirement. You'll be breaking the law if you don't put the whole on the right. To students who have developed that particular assumption, the equation that you see on this slide to them would just be wrong. You can't do that. You can't write 5 equals 2 plus 3. You have to write 2 plus 3 equals 5. We definitely want to avoid these misconceptions. They lead to problems, especially when children get to algebra. Equalities and inequalities are such an essential part of algebra. They really need to have a stronger understanding of an equal sign and get beyond the idea that an equal sign means that the answer is coming next. So in this case, the Common Core authors have strongly suggested that you use both add-in and known problems to give them some examples of seeing it a different way. So we started with a whole of 5 and we broke it into 2 parts, and so you can write the equation with the whole on the left. Compare problems are often thought of as how many more problems. That's really an oversimplification, though. There are 3 subtypes, as we've seen in the other classes, but here you'll see a lot of variation in language. There's the more language and the fewer language, so there's a number of language variants, and the children tend to struggle with the language elements. And then in addition to that, the relationships themselves feel a little more abstract to children. Finding out the unknown, conceptualizing the unknown difference between 2 quantities feels difficult for students to conceptualize. All right, we're going to take a look at the source of the difficulties for compare problems so that we can think about how to best support students. Background knowledge. If children do not have understanding of more than, less than, fewer than, then clearly they're just going to crash and burn when it comes to compare problems. So I strongly suggest at the beginning of the year playing games like more and compare, which I've included in teaching resources, both for Lesson A and Lesson C this week. As the children play, watch them and get a feel for how comfortable they are with these. Can they identify more than and less than? Can they quantify that difference? Being able to tell what they're struggling with, and it can help you in figuring out how to best support them prior to their work with the compare problems. Also, they need to have a capacity to represent a variety of situations through acting out. Some of those need to be in comparative situations. However, the variety of situations keeps students attending to the problem structure. You don't want children to get to the point where they pull numbers out of a problem and slap a plus sign between them because we're learning about addition right now, so I guess the teacher wants me to add. That kind of arbitrary thinking does not build a robust understanding of problem solving. So by giving students varieties of problems throughout, where even in the same assignment, they have to really attend to what's going on in the problem instead of doing them all the same way, that's going to be essential because they're really going to have to pay such close attention to compare problems that you need them thinking that they always have to be very attentive to what's going on in a word problem. The primary source of difficulty often, very often, for children who struggle with word problems is that they're struggling to visualize the relationships. And that's interesting for teachers to know, because if you encounter a student who's struggling, the first kind of thing you can think about doing is finding out whether they made sense of the problem. If they made sense of the problem, then the next thing you can do is help them to visualize the relationships using visualization tools. And in the case of compare problems, finding the difference between two numbers is really the essence of solving the compare problems, but conceptualizing what that difference means is very hard for learners. So in this example, this image is taken from the Common Core progressions. Julie has a quantity of 5, Lucy has a quantity of 3. It can be very difficult for me to visualize what would be the difference between those two numbers. However, you can see that the visual representations here show two possible ways to visualize it. I can either imagine that Julie and Lucy have the same, and then I imagine how many extras Julie has in addition to that, or I can conceptualize how many more would I have to add to Lucy's group in order for it to be the same as Julie's. In both cases, I see that differences too. But those two ways I just mentioned give the students a more clear-cut thing to imagine or visualize than just saying difference between numbers. Another source of complexity that adults often underestimate the difficulty of is pulling out information that's embedded in a problem. Children often just attend to the numbers, and the numbers themselves don't give them the clues for what to do with the numbers. They really have to look more carefully. Oftentimes, compare problems embed quite a bit of information into the same sentence, and so they really need to think about how to pull that out of the question. So if I were to have this particular problem for students and I want to introduce them to thinking very deeply about compare problems, I might give them the variation at the bottom. For example, on a smartboard, you can easily cover up numbers, or if I were just working with a whiteboard, I could cover them up with a Post-it, and I would give them the same problem like this, and I would tell them, you know, I've covered up some numbers here, and I'm going to read those as some. Mrs. Ray buys some pears and some oranges. How many more pears than oranges are there? And then I would have a bit of a chat. You know, when we problem solve, we don't just look at the numbers right away. We really try to make sense of the problem. So this problem's about Mrs. Ray, and it looks like she's bought some fruit. What kind of fruit did she buy? Did she buy more pears or more oranges? And then, you know, if they're not seeing the numbers, they can't use those numbers right away. Just say, what clues might be in this problem? I want you to study that, and then you can turn and talk to your partner and explain to them what you think and why you think that. You really want them to be able to attend to the question that's in orange and think about what clues are embedded in that question. And that's a comprehension activity that I strongly recommend for supporting learners with compare problems. As I mentioned earlier, there's just an incredible variety of wordings, not just the more than or fewer than, but also various language versions. So here, essentially, I'm getting at the same kind of an idea. How many cups will not have a saucer is more informal than how many more cups are there than saucers, which is the more typical word problem. Children who do not make sense of word problems very well will struggle with this, with all these variations, but they need experience with it. That's what's going to push them further to really make sense rather than developing superficial systems that will fall apart in future years. Now, not all of these language variants are of equal difficulty, and I use that to my advantage to gradually transition children into more formal and unfamiliar language of comparison. For example, I might bring actual cups and saucers into the classroom, begin with a brief demonstration, and use the top question. So how many cups will not have a saucer? That's an intuitive question that I don't think the students will struggle with, especially with the concrete materials. Then I might do several variations of that problem with the materials, and I might alter my language subtly each time so that at the end I'm using this language. So how many more cups are there than saucers? And that gets the students in the context of something real, seeing how their informal language connects to the formal language. The previous slide dealt with language variants that included informal and formal styles, but in this case you'll see the style is very, very similar. The wording is quite similar, but the problem structure is changing. The position or what is unknown is changing, and then some of them use the language of more and some of them the language of fewer. And we also see that the final problem, Jenny has 2 fewer books than Mary. Jenny has 9 books. How many books does Mary have? This is actually you have to add the 2. So that is a language variation that can be quite difficult. Children really need to know how to attend closely to problems and the relationships embedded in a problem in order to do this well. These particular problems will show up again in the presentation, and I'll give you some examples of how you can help students attend to the unique structures of each of these problems. The Common Core authors acknowledge that children are going to need extensive problem-solving experience with many problem contexts and variations in order to master all of these complexities, both the linguistic or language-oriented complexities as well as the situational, understanding the relationships between the elements in a problem and what the unknown is. But you can also look at these problems as unique tools or opportunities for your children to build a robust foundation in problem solving. By attending to all these variations and working through them and making sense of them and being able to visualize them, the children are going to build a very strong foundation for future problem solving. They will build that foundation, that is, as long as we can find some way for them to be successful. So saying that they're a great opportunity isn't all that encouraging if everybody's crashing and burning while they're doing them. So as a teacher, you need to have some systems, don't you, for how to support your learners. What can I do that won't interfere with their own development of problem-solving analysis? They have to learn how to do this for themselves. But if they're not already there, what can I do to help that doesn't take away the learning but is a true help and not something that's going to foster learned helplessness? So one of the things that you can do is to take a look at where the compare problems show up over the course of the year and think about who needs interventions and include that in there, and also be very thoughtful about how to build variation over time, how to start with some kinds of problems and then keep switching them, how to scaffold it in the same way that I talked about how the language can be scaffolded over time to get them from more informal comparison language to more formal. Another thing that you can do that we've talked about is really supporting them with visualizing situations, both by acting out problems with concrete materials and also through visualization tools like the number bond that I showed you and the tape diagrams. This is an example of tape diagrams, and here's 3 of those 4 questions that I showed you earlier, which had very, very similar wordings and context. But if you look at these tape diagrams down here, you'll see that every one of them involved Mary having 11 books. Every one of them involved Jenny having 9 books. Every one of them have a difference of 2. However, in each of these variations, you'll see that a different unknown is being asked for. So if you actually were able to build diagrams like this with your students, and you can use grid paper. I just take grid paper and I cut it into strips of varying lengths and laminate them and make them available to students. That isn't very helpful to them if I haven't spent quite a bit of time modeling how to use these. And then we can actually think about what each of these things represent. And so I'll say, okay, what does this one represent? Oh, that represented Mary's books. How many do you have there? 11. So how did that represent? Show me what you saw in the word problem that made you think Mary has 11 books. And so they're really having to go back and forth between words and model, and learning how to visualize that can help them build that strong understanding. Tape diagrams are specifically mentioned in the Common Core progressions. If you go to page 12 and page 16 of the link that I included earlier in the presentation, you will see